Okay, so we're going to go through the chapter 3 notes. And at any time, if you need to stop, if I'm going too fast, you can always pause. You can go back and listen to things again while you're filling in your notes with your partner. Okay, we're going to go through section 3.1 first, which is properties of matter. These are the objectives. Some review vocabulary. Okay, matter is anything that has mass and takes up space. So your matter, everything you see around you is made up of matter. Matter with a uniform and unchanging composition, that's called a substance. The physical form of matter, we can be a solid, liquid, or a gas. They each have their own properties, so let's go through those. Solids are a form that have their own definite shape and volume. Liquids, they have a definite volume, but they take the shape of their container, so kind of flexible in shape. You can pour them from one container to another, unlike solids that are rigid. Gases, they don't have any definite shape or volume. They're going to expand to fill their container. And a vapor, you can pretty much vaporize anything. Most of the elements on the periodic table are solids at room temperature. However, there are some gases that are on the periodic table that exist at room temperature, and there are some elements that exist as liquids as well. Actually, there are only two. It's bromine and mercury. But you can convert any of those from solid to liquid to gas by varying pressure and temperature. Physical property, that's a characteristic that can be observed or measured without changing the sample's composition. Here are some examples of some physical properties of common substances. Oxygen is color, is colorless. You know, color is a physical property of matter. The state of matter is a physical property. Its melting and boiling point and density. Those are all physical properties. And extensive properties, these are dependent on the amount of substance present, such as mass, length, or volume. Those are all extensive properties. Whereas intensive properties, they're independent of the amount of substance present, such as density. So we did density calculations before. Regardless of the size of the substance, you should come up with the same density every time. It's the amount of mass per unit volume. Now, if we're going to look at chemical properties, you have to observe chemical properties when one substance reacts with another. These are some examples of some chemical properties or chemical changes, and we're going to actually do a lab that's going to show you some chemical properties. You're going to observe some chemical reactions. Iron forming rust, copper turning green in the air. Those are some examples. A substance can change form. This is an important concept in chemistry. Chemical properties can change with specific environmental conditions such as temperature and pressure. So substances can behave differently depending on the temperature that they're at or the pressure in the atmosphere, things like that. These are some properties of copper. Physical properties would be things like color. Is it malleable or ductile, which mean most metals can be pounded into thin sheets, or ductile means they can be drawn into wire. Are they good conductors of electricity, densing, melting, boiling points, all that kind of stuff. So these are the chemical properties. If copper reacts, it can form a greenish color. And when it comes into contact with moist air, like the Statue of Liberty, or sometimes roofs of buildings are made of copper and they start to, it's called patina, turn like a greenish color. Form new substances when combined with nitric acid and forms a deep blue solution in contact with ammonia. So that brings us to how do we determine if it's a physical versus a chemical change? We're going to be investigating that a little further pretty quickly. All right, so density. This is a question for you to think about. What kind of property is it? The answer is it is an intensive property. Doesn't matter on the amount of the substance present, density will remain constant. And what defines a gas? Think about it. and gases do not have a definite shape or volume. Okay, so we're going to get into changes of matter. This is our second section. These are our objectives. Some new vocabulary. And we get to this. A physical change is a change that alters a substance without changing its composition. So let's say you're going to recycle an aluminum can. You melt the aluminum down, you reshape it into something else, it's still aluminum. So you haven't changed the chemical composition of the substance. So recycling would be an example of a physical change. Phase change is a physical change. So if you're going from a solid to a liquid to a gas, the substance is the same. You've just changed what state of matter it's in. So for example, if you have an ice cube sitting on a table and then the chemical composition is H2O, it's water, and then that ice cube melts on the sitting on the table. Now it's liquid water, but it's still H2O, still the same chemical composition. And then if that water evaporates or vaporizes into a gas, it's still H2O, but it's molecules of H2O floating around in the air instead of sitting in a puddle on the table or frozen as an ice cube. So boiling, freezing, melting, condensing, condensation, all of those are phase changes in chemistry. So a chemical change is when you have one or more substances that are changing into new substances. That's called a chemical change. So if you've ever cooked an egg before, that's a chemical change. You can't get the original egg back like it was to start with. So once something undergoes a chemical process, that can't be reversed. Burning a log, that's another example. So if you throw some wood on a fire, the wood burns, you have a pile of ashes left over, a bunch of light, heat, gases are given off during that process. That is definitely a chemical change. You can't all of a sudden scoop the ashes back together and recreate a log. So some more examples: decomposing, rusting, exploding, burning, oxidizing, cooking. They didn't mention that, but cooking is one. These are all chemical changes. Okay, now we're going to switch gears and talk about the law of conservation of mass. This is that mass is neither created nor destroyed in a chemical reaction. So if something undergoes a chemical reaction, you may end up with different products than you originally started with, but the original elements and the original reactants are still there somewhere. So they can be given off as a gas, they can be recombined into new compounds, but the amount of matter never changes. It's not created nor destroyed, it's just rearranged. So therefore, during a chemical reaction, the mass of the reactants equals the mass of the products. So if we have 2 carbons in the reactants, we have to have 2 carbons in the product somewhere. They just may not be attached to the same elements in a compound. All right, something to think about. When one substance turns into another, what kind of change has taken place? That is a chemical reaction. All right, the law of conservation of mass states that the products of a reaction must have the same mass as the reactants. Okay, now section 3.3, mixtures of matter. Here are some of our objectives. Some new vocabulary that will be introduced. All right, a mixture. This is a combination of 2 or more pure substances in which each pure substance retains its individual chemical properties. So we actually saw a mixture when we did the chromatography lab. You separated out a mixture of different pigments that all came together to form a black dye. A homogeneous mixture is where the composition is constant throughout. So let's say I dissolve the pure substance sugar with the pure substance water. That's a mixture. Sugar dissolves in water and forms a uniform, consistent mixture. Therefore, it is a homogeneous mixture. Same thing if I dissolve salt in water. You would form a homogeneous mixture. It's not separated at all. It's uniform throughout. Unlike a oh, I'm sorry, homogeneous mixtures are also called solutions. Unlike heterogeneous mixtures, this is a mixture where individual substances remain distinct. So if I were to mix oil with water, oil would float on top of water because it's less dense, and those two things wouldn't mix. You can shake them up, but then they're going to separate back out into layers. That would be a heterogeneous mixture. So here are some examples of some types of solution systems. You can have gas-gas mixtures, you can have gas-liquid mixtures, liquid-gas, liquid-liquid, solid-liquid, solid-solid. Normally you think of, okay, I dissolve a solid in a liquid and that's a mixture. You know, sugar dissolves in water. Well, that is one type of mixture, but you can also have a lot of different types of mixtures. The air that you're breathing right now is a combination of oxygen, nitrogen, and other trace gases. So that's considered a gas-gas mixture. You can also have gases dissolved in liquids, like when you have carbon dioxide dissolved in water, that's carbonated beverages. So if you drink a Coca-Cola or something, then and you have the CO2 bubbles in there, that is a gas dissolved in a liquid. So you get the idea, you can look at those examples. All right, yesterday we did a lab over chromatography, which is one way of separating mixtures. Some other ways of some other mixture separating techniques. One is filtration, and this is a technique that uses a porous barrier to separate a solid from a liquid in a heterogeneous mixture. Something this sounds too easy, but this is exactly what it is. Let's say I go scoop up some sand and water at the beach. The sand sinks to the bottom, the salt water is floating on top of the sand. If I want to filter all the sand out, I would pour that entire mixture through a filter of some sort, a porous barrier that would allow the liquid to go through, but it would trap the sand. Distillation, that's another separation technique. You've probably heard of distilled water before. What that does is take all the impurities out of the water. So what you're left with after distillation is pure H2O. And the way they do distillation is that they bring water to its boiling point, and that leaves behind all the salts or any other, calcium, magnesium, anything that's in the water leaves that behind, and just the water vaporizes, and then they condense it and cool it and capture the water. So distillation is a process to purify water essentially, and other substances as well. Distillation, fractional distillation, is used to separate oil from gasoline, different petroleum products and things like that based on their boiling points. And crystallization, this is a separation technique for homogeneous mixtures that results in the formation of a pure solid particles from a solution containing the dissolved substance. All right, that said in simple terms, let's say I have a beaker of salt water. If I let that beaker of salt water sit out for a while, or I put it on a burner and speed this process up, the water would vaporize or evaporate over time, and what you'd be left with in the container is crystalline salt, and that doesn't vaporize. So the salt would be remaining in the beaker, the water would be vaporized. That would be separation by crystallization. And you see in the classroom, we've grown crystals in AP chemistry. Or if you've ever had rock candy before, that's a process of crystallization as well, sugar crystals. Sublimation. This is a change in the state of matter that you may not have heard of. People don't talk about it very often, but sublimation is the process by which a solid changes directly to a gas. So it goes directly from solid to gas. And chromatography, this is the technique that we did in class, which separates components of a mixture on the basis of tendency of each to travel across the surface of another material. So the greater the tendency for a substance to travel across the material, the further it will spread. So you saw that some of the inks, some of the dyes spread further than others. That's one of the basis of chromatography. Another is molecular weight. So molecular weight can determine this, and attraction for those atoms or molecules to the paper that they're traveling across. Okay, so filtration, this is not a technique for separating a homogeneous mixture. You can separate heterogeneous mixtures through filtration, but not homogeneous. Okay, which of these is a heterogeneous mixture? The answer to that is D, salad dressing. So if you had like the oil and vinegar salad dressing, you know how it separates out, you have to shake it up really well before you use it. That would be a heterogeneous mixture because it separates unless continuously agitated. Okay, our last section is section 3.4, elements and compounds. These are our objectives. Some vocabulary they're going to discuss. All right, so what is matter made up of? Well, in essence, it's made up of atoms, and atoms are also known as the basic component of an atom is called an element. It's a pure substance. It can't be separated into simpler substances by physical or chemical means. There are 92 elements that occur naturally on Earth, and then there are some that are man-made. And I'll show you on the periodic table, at least the one that's in our room, all the substances that are black or red or blue are naturally occurring. Ones that are clear or white are not naturally occurring or synthetic elements. And we already learned that elements either have a one or two letter symbol. Three letter symbols are usually reserved for elements that they're newly discovered. And in the next chapter, we're going to discuss in depth the periodic table and its organization, but elements are actually organized in a specific way on the periodic table, so they weren't just thrown up there. There's actually a specific pattern. But the horizontal rows are called the periods and the vertical columns are called the groups. All right, so if elements come together, they form a compound. It's made up of two or more elements and they're chemically combined. So they can't be separated by normal separation techniques. You can't separate a compound by filtration or by distillation or chromatography. Simple phase changes, like when water goes from the liquid phase to the gas phase, that is not separating the hydrogen from the oxygen within the H2O molecule. You're separating one H2O molecule from another. So H2O is an example of a compound. Most of the matter in the universe exists as compounds. Most elements are unstable, you'll learn once we get into further chapters. There are very few elements on the periodic table that are completely stable by themselves. So they form chemical bonds with other substances to become more stable. Table salt, water, those are two examples of compounds. And elements, they can never be separated. But compounds can be broken into components, but it takes a chemical means of separation, not physical, like filtration or chromatography that we discussed earlier. You actually have to chemically break the bonds, and that requires energy. Okay, this is an example of breaking a chemical bond. So we can break apart the hydrogen from the oxygen, not through vaporization or evaporation, a normal process. You have to supply electricity. So this is called the electrolysis of water. It's where water forms hydrogen and oxygen through this process, applying electricity to the cathode and the anode. And you can trap hydrogen and oxygen gas through this process. So when we have a compound, it's different from its component elements. I'll show you later when we actually get to the properties of elements. Let's take sodium chloride, for example. Sodium chloride is made up of the element sodium. The element sodium is a metal, and it's a highly reactive metal. And the element chlorine by itself is a highly toxic greenish colored gas. And you mix the two together, a lot of light and heat is given off. It's an exothermic process. And in the end, you're left with table salt, which is sodium chloride, table salt that is edible. Neither sodium nor chlorine on their own are edible. You mix them together, they form a chemical bond, they become more stable, and then all of a sudden it's edible. So compounds have different properties than the component elements. And here's a flow chart of matter. Matter, we can break it up into mixtures or pure substances. And under mixtures, we can have heterogeneous or homogeneous mixtures. These are examples: dirt, blood, milk. Those are examples of heterogeneous mixtures. Lemonade, gasoline, steel, homogeneous mixtures. Then if matter is a pure substance, we either have elements or compounds. Elements would be things like gold, oxygen, iron, any element on the periodic table. And compounds are when we take two or more of those elements and bring them together, like salt, baking soda, and sugar. So we have pure substances and we have mixtures. And mixtures are two or more pure substances that are mixed together. All right, another definition. This is the law of definite proportions. This states that a compound is always composed of the same elements in the same proportion by mass, no matter how large or small the sample. So for example, if I get a glass of water, and assuming it's pure water, not some polluted tap water, it's just pure water. And then I go to another pure source, like let's say out in some Appalachian, or not Appalachian, yeah, let's say Appalachian Spring somewhere up in some mountains, and I get a sample of water from there, assuming it's pure, no other minerals or anything like that. Water is water, regardless of the source. Water always has the chemical composition H2O, and that means there are always two hydrogens and one oxygen for every water molecule. The relative amounts are expressed as percent by mass. So the ratio of the mass of each element to the total mass of the compound is expressed as a percentage. So if we're going to find the percent by mass of oxygen in water, you would take the mass of oxygen divided by the total mass of the compound and multiply that by 100. Okay, so we're not going to go through these slides. I'm going to pause this. Okay, now we're back to the law of multiple proportions. This states that when different compounds are formed by a different combination of the same elements, different masses of one element combine with the same relative mass of the other element in whole number ratios. So we'll discuss this further once we get to stoichiometry. And this ends our recording or our notes for chapter 3.